हिंदी में बात करना पड़ेगा, ठीक है? फर्स्ट ऑफ ऑल what is instrument? So basically instrumentation is what? Measurement, control. Control and instrumentation. Control and instrumentation. So control and instrumentation. This measurement can to control anything. You need to measure the parameter. Whatever you want to control, any kind of parameter. Parameter means what? It might be your level, pressure, flow, temperature, voltage, current, anything it might be. So whatever parameter we want to control, we have to measure it. So ये parameter control करना है, measure करना है. measure करना है. measure करने के लिए क्या करना पड़ेगा? measure anything, what we need. We have to sense it. If we can sense any parameter, then we can measure that parameter. So we need some sensors. So if we can sense anything, we can measure it, and if we can measure it, we can control it. Here, this much. Then this. Now, to control, we need what? We need controller. Need some kind of controller. That controller might be electrical type, electronic type. Basically, we are going to study on programmable logic controller and DCS system. PLC, or you can say the system, complete system, distributed control system. Study on this. Okay. Now, when I talk about the PLC and DCS, the confusion that comes in our mind is what is PLC, what is DCS? Whether they are completely different thing or what. But basically what? This is a control and this is a control. Whenever we are talking about some small number of IOs, then it is our PLC. Suppose I am talking about some machine control. I am talking about some machine control. Then it will be machine control. It will be PLC. Suppose you are having a packaging machine. Suppose I want to make some packets of some turmeric powder or say chips. So I need a simple machine to pack for packing. Then it is your PLC. PLC will be better. I will hardly need say 8 to 10 inputs. There will be some 4 or 5 outputs. So when I am talking about some few inputs and outputs, it is our PLC that can solve our requirement. And when we need to handle large number of IOs and interlink everything. Likewise in our power plants or refineries. So there are so many divisions and all the divisions are interlinked to each other. then it is better to go for a DCS, distributed control system. We can also say that distributed control system is a combination of multiple PLCs. You can have many PLCs and interlink each other, take everything to a single station and give it operators for. So this is the basic difference. Whenever I say PLC, it is small to large. A PLC can be as small as 2 inputs, 1 output, or something like this. But a DCS must have certain number of inputs. Otherwise, it will not be of use. It will not be cost effective. Now, what is there inside a PLC and inside a DCS? You can consider PLC as an industrial computer. It is an industrial computer. So whenever I talk about or we talk about a computer, we know that computer has a power supply. We call it SFPs. Because computer operates on the electronic circuit, operates on basically electronic devices operate on power good. Electronic chips, electronic devices, they operate on 5 volt, 0 to 5 volt. Electronic devices operate on 0 to 5 volt. Okay, and when we are taking some relays and transistors outside the circuit, we are making a circuit, then it is 0 to 24 volt. When you are trying to control some relays, then it is 0 to 24. Okay. So I need some power supply card. That is my SMPS. So when the supply is at 220 volts, and this supply card will be converting it into 24 volt, and it will be giving to the all its internal peripherals. Then internally, that 24 volt will be converted into 5 volt. 25 volt, and your electronic circuit will be operating. Here this one. Now to process everything, we need a controller, a brain, and that we call it CPU. We call it CPU, central processing unit. Just like our computer, we are having a CPU. But the design is something different from the normal CPU. Unlike our normal computer, we are having some I/O cards. But we are having instances, we are having some input/output cards or channels. This we do not see in our computer. Yes, we are having some input and output in our computer also. We can connect. What is the output in our computer? We can connect our printer. What are the inputs? We can connect some keyboard, mouse, scanners, etc. These are the inputs. What is the output of the normal computer? The printer. But we can handle other physical devices also through this computer. But we need some external peripheral devices and programming. Is that it? Those things are included in this. This is a industrial computer, and we are having some easy method to connect with the real-time environment, real-time devices. So we will be having digital input, digital output, analog input, analog output. Here this much. So this four kind of signals will be having in our field, and four type of cards will be attaching to our PLC. Other than these four cards, we might have some card for thermocouple and RTD. What is a thermocouple? What is a thermocouple? temperature measuring instrument element. On which principal thermocouple work? Silicon capacity. So if we are having two similar magnifier connected at one temperature and if there is a temperature difference or temperature gradient, then we can say that we are creating what? Voltage. Okay. So we will be having some EMF or voltage here. Can you tell me the range of this voltage? It will be in volt or kilovolt or something. It will be millivolt. It will be millivolt. Suppose a thermocouple. So I am having this. Can you tell me what are these? These are the temperature elements, temperature measuring devices, because they are having some step and some terminals. Can you please tell me which one is thermocouple, which one is RTD? कौन सा thermocouple है और कौन सा RTD है? Anyone? कैसे पता है? Which one is RTD? Which one is thermocouple? Which one is RTD? Huh? Both? Both are. So how to distinguish between the thermocouple and the RTD? How to distinguish? We have to look at the terminals. And RTD has how many terminals? RTD has three terminals. We use three-pair RTDs. Normally, we use three-pair RTDs. Okay, and thermocouple two-pair. So a thermocouple will be two-pair, and the RTD will be three-pair. In the symbol of the RTD, this is your thermocouple. Now, what you have seen here? Terminals. There are six terminals. Is that in the black one? There are six terminals, and the yellow one there are four terminals. Then it is called duplex thermocouple and duplex RTD. Duplex thermocouple and duplex RTD. Okay, means there are two RTDs. There are two RTDs and two thermocouples inside this case. Here, another way to identify the thermocouple and RTD is you can see that in our thermocouple there will be plus and minus. Since we are getting millivolt, and this is called DC millivolt, so there will be plus and minus sign. But in RTD, it is a single wire, single which material we are using in RTD? platinum. So we normally use in our industry platinum 100. Then so points. We use PT 100 in our RTD. And what type of thermocouple we use? We use K type thermocouple. K type thermocouple. When I say K type thermocouple, that means the two materials that is selected is chromium and aluminum. Chromium and aluminum. The two materials are chromium nickel and aluminum nickel. Chromium nickel and aluminum. What will be the range? The range will be up to 1200 degrees. So data transfer works up to 1200 degrees centigrade, minus 2 or 0 to 1200 degrees centigrade. So normally this much temperature is sufficient for a furnace or in power plants or in big industry. This much range is okay. If you are having some higher temperature, say 1500, 1800, then it will be different, right? But normally we use another point is when we will be using RTD and when we will be using thermocouple. What basis you will be preparing thermocouple? For higher temperature, RTDs. Okay. RTDs for higher. Thermocouple is for higher. RTD, the rate of RTD is say up to 300 or 400 degrees. We are sorry, below 300 degrees you can prefer RTDs. When you are measuring above 300 degrees, better it is thermocouple. So for higher temperature we use thermocouple. What is the something simple? One is we can show one resistance in the path of the RTD and two common. This symbol means two lines they are common. What is RTD? It is nothing but a wire. It is just a wire. How it is working? What is the working principle? That with temperature, the resistance of pure metal varies directly. That means we are using what type of material here? We are using positive temperature coefficient metal. Temperature, there are three types of temperature coefficient. One is positive temperature PTC, one is LTC, negative temperature coefficient, and one is ZTC, zero temperature coefficient. So we are using PTC materials, means pure metal. Pure metal and some alloys are metal alloys are positive temperature coefficient materials. That means with increasing temperature, the resistance of the material increases. If the resistance decreases, there will be negative temperature coefficient. Likewise, what are the NMC materials? Likewise, all non-metals, insulators, electrolytes, your semiconductor devices. Why they are negative temperature coefficient? In case of semiconductor, you put it in the absolute zero temperature, they will be behaving like an insulator. You raise the temperature. When you are raising the temperature, suppose you are taking it to the room temperature, then thermally generated electrons and holes. Yes. Okay. When it is at 300 degree, so thermal generation started at 220. So here, since the electron and hole pairs are coming into the they are conducting the current, that means the resistance is decreasing, conductivity is increasing. Are you getting my point? So those kind of material whose resistance decreases with temperature are called NTC materials, negative temperature coefficient materials. Those materials whose resistance increases with temperature, they are called PTC material, positive temperature coefficient. Who all are positive temperature coefficient materials? All kinds of metals and their alloys. Most of the alloys. There are some alloys which do not change their resistance with temperature. Whether it increase the temperature or decrease the temperature, the resistance of the material will not change. Those kind of elements are called materials are called ZTC materials or zero temperature coefficient materials. Likewise, our Eureka, manganese, and constant. Eureka, manganese, constant. Okay. So if it is a wire and its resistance is changing, you can measure the resistance and compare it with the temperature variation. Now we have seen that there will be lead wire that is coming from the field effluent, taking the lead to the control room also some distance. So what will happen? There will be some error. To minimize that error, what we do? We use 3-wire or 4-wire compensation. 3-wire compensation or 4-wire compensation. So 4-wire compensation is not required in all industry. 3-wire compensation is sufficient. So you can see here the two terminals having zero resistance input. They are shorted, they are common. And one terminal is having some resistance with respect to this terminal. Okay. That is why we represent RTD as one strand with resistance, another as common. When you will connect some multimeter here, you will be getting resistance between these two. You will be getting resistance in between these two. And you will be getting zero resistance or short. Thermocouple. Clear this one? Now you can see what is in my head. I can see here that one is having 6 terminals, one is having 4 terminals. So 4 terminals one will be thermocouple, 6 terminals one will be RTD. Clear this much? Another thing we can notice that you can see here that 2 terminals of this RTD is having same color, white and red and blue. 2 terminals are having white and blue. Check. Is that it? And one terminal is blue and white. So 2 white are covered and 2 white along with the red. This is one item. 2 yellow along with the blue. This is second item. In case of thermocouple, you will see there is a plus and a minus written on the terminals. Mark here. Here. Now you can if you say if I am having an RTD say duplex RTD. Having duplex RTD is how many terminals? 6 terminals. So I am having a duplex RTD, 6 terminals. Say I am having a thermocouple, triplex thermocouple. Okay, we are having triplex thermocouple. how many terminals you get? So we can go with the color coding. Otherwise, there is no level. No level. Clear, everyone? Clear? Okay. Now you see. I am having this thermocouple in my hand. Can you tell me how much millivolt? Okay. How much temperature it will be showing, or how much millivolt I will be getting in the two terminals? Positive and negative. How much millivolt? We have around 20 degrees centigrade. 20 degrees centigrade. How much millivolt? Anyone? So 0 millivolt. Right? So just think and let's check. No. Voltage difference. Are we applying any voltage in the thermocouple? It is generating voltage. We are not applying voltage. It is generating voltage. Then what happens is, see, you have forgotten the principle. Basic principle. Principle says that whenever there is a temperature difference between the two terminals, when I am holding it like this, is there any temperature difference between the two terminals? Then if delta is 0, the milliwatt is 0. If I touch it here, now you will get some milliwatt. It will be showing like positive. You put it on the hot bar, put some temperature here, then you will be at the terminals and it will be showing some millivolts. And we are having some standard chart available on. From where you can calculate, or you can calculate it by knowing the resistivity of the temperature coefficient, and then you can calculate. But when you calculate, there are standard chart available. I will be afterwards that okay. Give some temperature, how much millivolt comes. So we by using traditional RTD thermocouple. Since RTD thermocouple is generally used, basically the PLC text as analog input as analog input PLC milliampere 420 milliampere and it is giving us milliampere. So either you have to connect some, then I have to connect some temperature transmitter, or some milliwatt to milliampere converter, and then I can connect it directly to my analog. This temperature transmitter will convert this millivolt, that millivolt is generated by the thermocouple to milliampere, and the analog input will be at 4 milliamperes. Then you can connect it to the analog input card. Otherwise, you have to insert additional thermocouple card. This card is converted to this one. Getting my point? So what we have understood? We have seen that PLC is an industrial computer. Similarly, it is having a CPU, power supply, and some cards. What are the different cards? Another card. There are two additional units for RTD. We have understood RTD is nothing but a wire, metal wire, and the metal is nothing but platinum. But what is the model number or say type? We 100. That means at 0 degree centigrade, the resistance of this is 100 ohm. And then we start our calculation. But it's thermocouple is nothing but similar rectifier connected at junction. So this is what we are doing. Okay, this much is clear. Now, with the understanding the control, prior to that, we have to clear our idea on electrical connections. Electrical connections. Hardware. That hardware level control, when I say contactors, and we will be developing some control circuit and power systems. Okay. So very similar name to this. I am not directly jumping to the automation part, but a bit about circuit and your control circuits will be good. Now, whenever we talk about electrical control circuit, we use some instruments. And push button means switches that can make or break when you push it, and when you release it, it comes to its own position. So there are two types of push buttons: analog push button and LC push button. Normally on and normally hold. This is an analog push button. This is a LC push button. LC means normally closed, NO means normally open. there are two types of push buttons. The push button, what is this? This is open. Normally open. Normally in that normal position it is open. When you push it, it will make the circuit. It will allow the current to flow. And this is what? This is LC. LC is normally closed. So it will allow the current to flow continuously, and when you push it, it will break the circuit. That's simple. Is that it? So we'll be using normally open push button, normally closed. I'm showing you right now. Another thing that we are going to use is called contactor. What is a contactor? A contactor is nothing but a switch, electrical switch that can make or break multiple circuits at a time. That can make or break multiple circuits, two or more circuits at a time, and all the circuits are electrically isolated to each other. All the circuits are electrically isolated to each other. All the circuits can be made and break at a time, but they are electrically isolated. Okay. So how to operate this? Suppose this is a switch. There is another switch. There is another switch. There is another switch. There are four switches. And I want to make all the four circuits at a time. So what I can do? I can connect all the switches and pull it. I cannot pull it manually. What I can do? I can connect a coil here and send some electrical current. This current will create a magnetic field here, and this magnetic field will pull the armature. Now, if these contacts are N, and these two contacts are M, N will become O, and S will become open. Whenever this coil will be energized. Whenever this coil will be. So, it is having this one as our control circuit, and this can be used as power. I can power up 1, 2, 3, 4 circuits at a time. So based on the contactor, based on the number of inputs, okay, and the multiple circuits. Otherwise, this is a contactor. So what is the circuit symbol? Circuit symbol for this coil is electric current. This is this. So the coil. This is the coil of the contactor. And name it as A1, A2. The two terminals are named as A1. So whenever there is a coil set it is in linear or it is in timer or it is in contactor, we will be named as A1 and A2 terminal. Let's see here. A1. The other one. This is like A1 terminal. So we will be giving supply here. How much supply we will be giving? It will depend on the coil of the contactor. It might be 24 volt, it might be 110 volt, it might be 220 volt AC. So it will be depending on the coil of the contactor. We have to select which contactor I want to measure. So this is a 220 volt 15 hertz contactor. Other thing is that this is a 4 anode type contactor. 4 anode type contactor. So L1, P1, L2, L3, L3. You might be thinking that why L1 and PLC and certain areas. So wherever we this is the standard communication. This first digit represents the number which contact number of four other contact, and this is actually your start at the circuit. So L1, L2, L3. These are the three terminals. And this one shows the number of contacts. 1, 2, 3. And the second digit, 4, represents 1 and 2. 1 and 2 represents that's the second. Yes. 3 and 4 represents L. That means suppose this is number 1, number 2, number 3, number 1. This is L. This is your L. So it is this is the LC. This is the LC. LC 1, 2. One. That is the number. Which number of position of the number. Likewise, this is 1, 2, 3. So I have 4 contacts. So 1, 2, 3. The second digit is representing whether this contact is yellow or orange. So this is 3, 4. Means likewise when you will see which of the terminals you will be finding this kind of numbers. The 30, 40, 31, 32, 31, 32, 41, or 43, 44, or 41, 40. So how it is something else you have 30 and 47. And then it is not 15, 16, it is 21 and 20. But this is S. 1, 2, 3, 4. There are 4 contacts. So this is the position. And 3 and 4 is for yellow. 1 and 2 is for S. Right? And I will be documenting that point. That is connected to 21, 24, 31, 32, or 43, 44. Hasan? So coil is represented by A1 and 2 terminal and contacts are as 13, 14. Now to control electrical energy, control is square. We will control this square supply and this object So straight away I'm coming to our model. What kind of motor we are using in this? What kind of motor we are using? Induction. There are two types of induction motors. What are they? Either it is a slip ring. Slip ring induction motor है. Squirrel based induction. So we will be using squirrel based induction. This is how induction motor works. So induction motor works on the right now we see if it is a three-phase induction motor, then how many terminals will be getting? How many terminals will be getting? 6 terminals. Three-phase induction motor. Since three-phase means there will be 3 coils. Okay. 3 coils. 3 coils means 6 terminals. Now you can connect these terminals as star or delta. Star or delta. What is the nomenclature? How will you do it? What? V1, second place, and W1. W1 is the third place. W. Can you tell me if I am having two identical motors, just by looking at them, can you identify which one is single phase and which one is three phase? One is three phase. Just by looking at them, you have to tell me which one is three phase and which one is single phase. That means what will you do? Suppose terminals is not. The single phase machine, single capacitor connected. Single phase motor, a capacitor connected. Terminal box. Three phase induction machine will have a terminal box, whereas the single phase machine will have a condenser or capacitor connected. Okay, so you can simply see the single phase. This is the. Now, when I open this terminal box of the three phase machine, what I will see? I will see 6 terminals. 6 terminals in the 3 coils. And how they are arranged? They are arranged as U1, V1, W1, and U2. But just see what it is. That's all. Why it is arranged like this? That U1, U2, V1. for different voltages. You are using a secret induction motor and you are different voltages at different terminals. What are the reasons? You can simply arrange it like one into it is for the ease of connection. Likewise, if I connect this or start and same thing. Short like this. Get that? So this is my P1. So you use feedback of this one connected with the star connection. So see what is position is for potential voltage. Rotating magnetic field can only be produced when the temperature some three-phase balanced frequency. When a balanced three-phase winding, remember this line, or you can write when a balanced three-phase winding, right? When a balanced three-phase winding displays in space by 120 degree. When a balanced three-phase winding displaced in space by 120 degree is supplied from a balanced three-phase current displaced by time displaced in time by 120. Then a rotating magnetic field is produced. Which rotates in space in synchronous speed. And the direction of rotation is same as the phase sequence of the sun. And the direction of rotation is same as the phase sequence of the sun. When a balanced three-phase winding is displaced in space by 120 degrees. Here are my balanced three-phase winding displaced in space by 120 degrees. Is supplied by from a balanced three-phase current displaced in time by 120. So current is displaced in time by 120 degree, and the coil is displaced in space by 120 degree. When they are meeting, the rotating magnetic field is produced, and the speed of the rotating magnetic field is same as your synchronous speed, and the direction of the rotation is same as the phase sequence of the supply. That means if I interchange the phase sequence, the rotation of the induction motor will be opposite. Suppose I am connecting this motor. As the machine is rotating, I can change the rotation of the machine by interchanging any two phase. Any two phase. I just interchange two phase, and the rotation of the motor will be the opposite phase. Is my point? So we can just interchange the two phases, and the rotation will be here. When a balanced three-phase winding, so this is the stator of the motor. Now I am having three phases. So three A phase is A dash. What is 1 point? From this A phase, the B phase will be 120 degree in space. 120 degree in space. 120. And B phase will be coming here. Second terminal B dash. A dash. This is 1 point. B dash. This is second point. Okay. From this B phase, the C phase will be 120 degree in space. So 120 degree in space. Somewhere here. So the 6 terminals I can see. Now, what I will do, I will be shorting this B dash as three terminals I will shorten. So it is start connection. Now I am feeding it with three-phase balance supply. Three-phase balance supply. Balance supply is this is one phase, this is second phase, third phase. Y, now, if you understand the three-phase supply, well, suppose this R phase is having the maximum current. At that time, the other two will be having minus IM. Because IR plus IR balance. So when my IR is maximum, IM. So IM is coming in, out, and then going into penetration. The two penetration are having balanced circuit, so having same impedances. So this will be my IM by 2. This will be my IM by 2. The IM by 2 is coming here. It is coming here, so it is moving from the terminal. The direction is this. This is coming here. So it is going out from this terminal. So it is going. So when my IR is maximum, so I can see here IY is leading, that is minus IM by 2, and IB is also minus IM by 2. Yeah. So that's IM minus IM by 2 minus IM by 2. Now we have what we have done? We have created three-phase winding. We have placed three-phase winding 120 degree apart in the space, and we have supplied this three-phase winding by a balanced three-phase supply. The current is displaced in time by 120 degree. Current is displaced in time. In first, IR will be maximum. After that, IY will be maximum. After some time, IB will be maximum. So this this three-phase supply is balanced. Okay. Now we can see If this current is going in, so what will be the magnetic field? The direction of the magnetic field will be clockwise. If this is going in, so the direction of the magnetic field is clockwise. This is going in, so the direction of the magnetic field is clockwise. Since it is an iron body, so all the magnetic field will be going choosing the path through this stator and coming out, cutting the rotor and going. So this is the similarly you can see here the flux is in this direction, the flux is in this direction. So ultimately, okay. Now you can see in the stator, the flux is entering in this point and leaving from this point. Isn't it? So the part of the iron from where the magnetic lines of forces or magnetic flux coming out is called North Pole. The part of the iron from where magnetic flux is coming out is called North Pole. So here from the metal flux is coming to here. So this is North Pole and this will be South Pole. Where it is here, it is called South Pole. North Pole. After some time, this VDR should be maximum. When this VDR should be maximum when current is in, current is in, maximum current is in. Suppose it is rotating, or you can say, so this is in, current is in, and maximum current is here. So if it is in, the maximum current is in. This is giving IM. So if this is IM, so this will be my IM by 2. And this will be also IM by 2. Is that it? If this is coming, this is also coming to them. I by 2 plus IM. Now you see, if it is so, the current is leaving from NS now. Current is leaving from NS. Current is leaving from B. Current is leaving from B dash. Current is leaving from your C dash. Are you getting the point? This is IM by 2. This is IM by 2, and this will be IM. So if it is IM by 2, that means the current in here will be IM by 2, and if IM by 2 is coming in this way, so it is coming out. Current is coming out, IM by 2 current, and it is coming out, and C. The direction will be opposite and current will be I plus. So IM by 2 current is coming here. Got it? First part we have considered. First one is here. Now, after say 60-degree rotation, it is taking some 3.33 minutes. The magnetic field is shifted. So maximum current is here. If maximum current is here, that means IM. If this is ion leaving, that means this is B from B. It is coming out. Here it is coming in, from B it is coming out. This much clear. Now if my B phase is having this current, that means A phase is having IM by 2 leaving from K dash and coming from IM by 2. So incoming is IM cross, outgoing is dot. So IM by 2 is coming in and IM by 2 is leaving. See that? Since this is IM, so this is IM must be IM by 2 coming in this, and that means coming out from C dash and coming in from C. So from C, IM by 2 is coming in and going out of C dash. They are meeting at this point, and IM by 2 plus IM by 2 and coming in. From C, the IM by 2 current is entering. From C dash it is leaving and coming to the common point, start point, and going to the. Okay, now it is clear. Now you can see my cross has changed this position. Previously it was this tree, now it is this tree. So the magnetic field will be from here. I can see this and this. Magnetic field. So this part on the north pole now. So your south pole was here, now it is here. Your north pole was here, now it is here. So your north pole and south pole is here. That means the magnetic field is rotating. After 3.33 milliseconds, this north pole will be coming here, coming here, coming. That's the way how we are doing it. Rotating magnetic field. And since the field is rotating, we'll be putting one squirrel case rotor. Squirrel case rotor means a rotor which is closed from both sides. So whenever a rotating field will cut the closed circuit, an induced EMF will be induced rotor, and that induced EMF will produce another magnetic field, rotor magnetic field. Now this is my stator magnetic field which is rotating. This rotor will be having some EMF induced due to the rotation. Suppose this rotating magnetic field is rotating at a speed of ns. The field will be rotating at a speed of ns, synchronous speed. Okay. Now this synchronous speed, the rotor is static. The rotor is static. That means the speed is 0. So what will be the difference? Speed difference? It is ns. ns minus 0 is ns. So delta n is ns. Delta n is equal to ns minus 0. That means there will be some induced EMF, and this induced EMF will allow to flow a current inside this rotor so that the current can produce another magnetic field to oppose this rotating magnetic field. It is due to Lenz's law or inertia. Inertia. Since the rotor is static, it will continue to move. Now the magnetic field is rotating. This magnetic field is coupling with this. So due to this rotating magnetic field, the dipole inside the rotor will change in their orientation, and an induced EMF will be produced inside the rotor. That induced EMF, the direction of that induced EMF is such that it will allow a current to flow inside the rotor so that another magnetic field produces inside the rotor, and the difference should come. So the rotor will start moving in the same direction to catch this rotating magnetic field, And suppose the rotor is start moving at the speed of nr, so the difference of speed will be ns minus nr. So the rotor will start moving higher and higher to catch ns, but it will never touch. And this part is called your slip. Right? That's what. This part is okay. These are all some of theoretical lessons that we are working on process. I have just explained it because the reason I have what I have given you just now. It is whenever stick is pointing display is by 120 is applied by a three-phase balance current, which is displaced in time by 120. Then rotating how rotating we have understood. You not need to go or just it is the best kind of I have understood how induction motor is working. Okay. Now, what we need to connect the terminals. These terminals. We have to build the induction motor from a three-phase system. And how can we change? We can connect it in star or in a delta. Okay. So the starter, you make a starter for this induction. The starter may be direct online starter or star delta starter or soft starter or VFD variable frequency. That the two types of starter that we use for to start our induction motor. Start our induction. When we use the dual starter, dual means direct online starter. Direct online starter. When we use direct online starter, if your motor is small rating, direct online starter, dual starter. And usually we connect the motor in star. That means we shorting the W2, U2, W2 and V2. Short U2, W2 and V2. Come and start connection. And to simply feed from a three-phase supply, the motor will start a star. Normally we avoid delta connection in dual circuit because why? Why we do not use delta connection direct online? While enough, what is the reason that we do not connect induction motor on delta? So the starting current in delta is approximately 5 to 7 times the normal working current. Starting current is higher. Starting current in star is also higher than the normal working current, but it's about 1.5. Whereas in case of delta, it is 5 to 7 times. Thus, we avoid starting a motor in delta connection and start in star connection. Now the loss in star is higher than loss in delta. I will be able to show you later how the loss is higher in delta. So loss is higher in star. So loss is higher in star and starting current is low. So for bigger motors, we will be using star delta circuit. That means we will be starting the motor in star connection and then we will be changing it to delta. So this is called star delta connection. Understood? So there are 4 types of starter. We are discussing. Number 1, direct power. Starting the motor in star connection. Star delta will be starting in star, then we will be converting it to delta, and other two are soft starter and VFD. So soft starter is electronic starter. That is basically your star delta starter, but it is coming compared to starter and VFD. Another one is a VFD. VFD is variable frequency drive. Variable frequency drive. Why we use VFD? For speed control. For speed control. Variable frequency drive is used for speed control. Because the speed control of the induction machine is very challenging. You cannot control the speed. We have to control the supply frequency. Then we can control the speed of the induction machine. That is my point. So the speed is depending on the synchronous speed of the machine. Rotating magnetic field is rotating at synchronous speed. Thus, we will be changing the frequency so that the rotating magnetic field speed is changed, and thus the induction machine speed. Okay. So to control the speed, we will variable frequency. Soft starter is an electronic starter. It's just a starter, but now we'll be learning how to make one starter, then starter the starter. How to start an induction machine from local panel, from field, and from control to electrical. How we can on this or control this motor for speed from our PLC or DCS. What are the sensors we will be using to or connecting the motor to find out whether the motor is running or it is stopped or it is tripped. So what is the speed of the motor? How much speed we want? We have to give some command to the controller that okay, I want to run the motor at 50. Say the RPM of the motor is 3000 now. 3000 RPM. The motor is running, but I do not need this much RPM. I want to some lower RPM, say 1500. So I have to give some command. So how I can give command to the PLC? What are the configurations that I need to do in my software or PLC? How can I see that what is the how much RPM it is going on in the field? That we have to look at that. You can see here that those pictures. See, those pictures are your SCADA pages. You can see If you go to any control room anywhere, in refineries or in power plants, you will be seeing that yes, and they are now, based on the pressure and temperature, I have to control the feeding. Based on the pressure and temperature, I have to control the feeding. So, I have to how I can control the feeding? I can control the RPM of the feeder. So, when the feeder will be rotating at a lower RPM, it will be getting some lesser force. We will be using some pocket feeder. So, we will be taking some support. And it is having some bucket. So one bucket. The speed is more with 4 buckets of fluids are doing just with lesser buckets of fluid. The speed of the fluid. The control makes the pressure and temperature. So how to design this? How to configure this? That will be learned. Another thing you can see here, there are motors, IDPH motor, there are PLC motor, temperature motor, heat pump. So everything is motor. This is a motor. This is a pump, but this is a air. But we are putting a motor. So how to start this fan from my panel? If this motor is stripped, then this motor should work automatically. How to make that circle? First, get the theme what we are going to learn. Suppose this ideal one is running right now. That ideal is stopped. Now, suddenly, ideal one is stripped for any reason. Ideal must on. Similarly, there are interlocks. Interlocks means where ideal will be tripped. PML will be tripped. FTL will be tripped. Your consider will be everything. The whole bottle. This is for interlock. Like interlock. But I say when ideal is tripped, your PML will be tripped. When PML will be tripped, FTL will be tripped. When FTL will be tripped, consider will be tripped. So this is the interlock. The whole bottle will be tripped. Now to switch on once again, light up once again, or start the feeders, you have to first you have to start the idle. If idle is not running, you have to start. When time to start the idle, so how is it done of the feeder? You have to understand this. Next, when you start the idle, then start the feeder, then start the feeder. Then you have to ensure that your space is out. Then you have to go to the there are so many interlocks in the boiler box, and you will understand this. Simultaneously, we will see that there are parameters like harnesses, like splitting output, like what will the generator R is here, Y is here, so current is showing here, temperature is showing here, configure RPM is showing here, harness temperature. These things we are collecting from our field. There's so many parameters. So how we are collecting? So when have to learn each and every parameter separately. How much time it will take? But not take that much time. Because you understand that what is the procedure, then it will be like what you will have to learn, you will learn the basic electrical science, how electrical connection are made. Then you have to learn how you can improve the this is where the PLC and DCS, how you are configuring the parameters, what is the set points. Another thing is, if you are streaming for a job in a power plant, then you have to know power plant. You have to know turbine control. You have to know boiler control, boiler logics, boiler. Otherwise, it is difficult, much difficult. It is much difficult. You cannot learn in a day. Boiler control, turbine control. Most complex process. You have to see boiler, steam turbine. So our first target will be we have to understand this is basic circuits, electrical circuits. Then we'll be doing some hands-on on PLC programming, small programming, machine control, and then applying the power. Okay. So I hope this much is sufficient for today.